Okay, let's go to page 303. This is lesson 5.2, and this lesson is to use perpendicular bisectors. Okay? So in lesson 1.3, you learn a segment bisector intersect a segment at its midpoint. So here's your perpendicular bisector. Perpendicular bisector is perpendicular to the segment and also goes to the midpoint. Right? See the word bisect. Bi means two, sec means cut. So bisect means cut into two equal parts. So that's what bisector means. And it's perpendicular. Okay? So a segment, ray, line, or plane that is perpendicular to a segment, so it's perpendicular. And you can tell by this symbol right over here, this tells you that it's perpendicular. So it's perpendicular to this segment at its midpoint. Okay? This is midpoint because see the marking means that equal length. So this is the midpoint. Okay? So this is a perpendicular bisector again because it's a right angle and it cut into two equal parts. Okay? A point is equidistant from two figures if the point is the same distance. So again, equi means same, distant means, or distant means distance, right? So equidistant means same distance from each figure. So like the point C would be equal distance to the A and the B, okay? So points on the perpendicular bisect a segment are equidistant from the segment's endpoints. So what it's saying is that every single point on the perpendicular bisector would be equidistant to the endpoints. Okay, whether it's over here, see if it's over here, it's very obvious, right? Okay, if over here it's less obvious, but that's the theorem. You can prove it later on. Okay, so again, so point C is equidistant to point A and the B. So any point, okay, any point on the perpendicular bisector, any point on this line will choose any random point on the line, it will be equidistant to point A and B. Okay? Okay, so that's your theorem. So theorem 5.2, perpendicular bisector theorem. It says in a plane, if a point is on the perpendicular bisector of a segment, so any point on the perpendicular bisectors, okay, then it's equidistant from the endpoints of the segment. So again, any point will equal distance to the endpoints. So any point on the perpendicular bisector, like point C or point P or any point with equal distance is equidistant from point A and B. Okay? Now, the converse, theorem 5.3, converse of perpendicular bisector theorem is just the opposite, it's just the converse. That if a point is equal distance to the two endpoints, then the point would be on the perpendicular bisector. Okay? So in a plane, if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of a segment. So again, if a point is equidistant to the two endpoints, then it's on the perpendicular bisector. So they are kind of the converse of each other. Okay. So this one, if it's on the perpendicular bisector, then it's equidistant to the endpoints. Over here, if it's equidistant to the endpoints, then it is on the perpendicular bisector. Okay. Okay. So over here, to use that to solve. So in example 1, so BD is the perpendicular bisector. So here's your perpendicular bisector of that. So that means any point will equal distance to the point C and A. So equal distance means these two are equal. Okay. So if the two are equal, you set it equal to each other. Okay. And then you minus 3x on each side. So you got 2x equal to 14, and then you divide by 2, you get x equal to 7. Okay? Once you find x equal to 7, you substitute into here. 5 times 7 give you 35. Okay? So AD equal to 35, CD is also 35. Okay? So you can use the perpendicular bisector theorem. You set it equal to each other, and you use your algebra to solve. Okay, okay, let's go to page 304. Okay, example 2, use perpendicular bisector. In the diagram, okay, line WX, so WX is perpendicular bisector. Okay, okay. So what segment lengths in the diagram are equal? Well, if this is a perpendicular bisector, then YX will equal to XZ, right? Also, YW will equal to WZ, and also VY will equal to VZ because this is a perpendicular bisector. And it shows you, right? The reason this is two equal already because it shows you over here, right? Okay, so what's segment length and diagonal are equal? Again, I just mentioned, right? So this is equal to that, this is equal to that, this is equal to that. Okay? Now it says, so next question is V, is a point V on the line XW? The answer is yes. Because see the point V is equidistant from the two endpoints. See the 25 and 25? Since they are same length, so it must be, the point V must be on the perpendicular bisector. Okay? Okay, so next one, let's go to the next topic. Okay, so on page 305, concurrency. It says when three or more lines, ray, or segment intersect in the same point, they are called concurrent lines, rays or segments. Okay, so the point of intersection of a line, rays or segment is called a point of concurrency. So like when you have more than like three or more lines or segment or whatever, they meet at one point, that's called a point of concurrency. Okay. So with that in mind, so let's go to theorem 5.4. Concurrency of a perpendicular bisector of a triangle. Okay. So the perpendicular bisector of a triangle intersect at a point that's equidistant from the vertices of a triangle. Okay. And so over here it says if PD, so PD, PE, and PF are perpendicular bisectors, then PA equal to PB, PB equal to PC. Okay. So again, what this is saying is this. Okay. So if you look at this diagram over here, this is on your handout. So when you, it's like this over here, see this, you draw the perpendicular bisector, right? So remember, perpendicular bisector, any point will be equal distance to the endpoints, right? So let's use this point, let's call it center point, the point of concurrency. So this point is equal to this point, equal distance to this point. And you rotate the same thing, right? So this point equal to distance to that, equal distance to that, okay? So this is point equal distance to that, equal distance to that, okay? Now since this is equal distance to all three vertices, if you notice, this becomes like the radius of the circle. If you draw a circle, right? This would be like the center of the circle, and this would be the radius, this would be radius, this would be a radius, okay? So the perpendicular bisector of a triangle meet at a point called a circumcenter. Circum means going around, okay? So the circumcenter is the center of the circle that go around the triangle, okay? So again, when you have perpendicular bisector, it will meet a point called a circumcenter. And again, circum means around, okay? So center is a center of the circle that go around the triangle, okay? Okay. So let's go back to the book, okay? So example 3, use concurrency of perpendicular bisector. Okay, frozen yogurt. So 3 snack carts sell frozen yogurt from point A, B, and C outside a city. Each of the 3 carts is the same distance from the frozen yogurt distributor. Okay, so the distributor is over here. Find a location for the distributor that is equidistant from the 3 carts. Okay, so again, the way to do that is, okay, go back to, okay, they have this over here. Okay, so again, you got 3 points, right? To find a point that's equal distance from all 3, you use a perpendicular bisector. Because from here, this perpendicular bisector, you will make this point equal distance to A and C. Use this perpendicular bisector, okay, and use this perpendicular bisector. So all 3 will meet right over here. That means this distance, this point D is equal distance to B and C, and it's equal distance from B and A, and equal distance from A and C. Okay? So basically you apply the perpendicular bisector for all 3 sides. Okay? Again, this is called a circumcenter. Okay? Okay. Now let's go over here. Let's go to page 306. Circumcenter. The point of concurrency of the 3 perpendicular bisector of a triangle is called the circumcenter of the triangle. Okay. The circumcenter P is equidistant from the 3 vertices. So again, this point is equidistant to 3 vertices. So P is the center of the circle that passes through all three vertices. Okay, so again, this is the center of the circle that goes through all three vertices, because this point is equidistant to all three corners or three vertices. Therefore, this is like the radius to all three vertices. Now, the circumcenter would be inside a triangle if it's an acute triangle. So for acute triangle, the point P is inside the triangle. For the right triangle, the P is on the triangle, and also it's on the midpoint. Okay, so if you are right triangle, then you find the midpoint of hypotenuse. That would be the center of the circumcenter. Okay, so again, if you are right triangle, you find the midpoint of the hypotenuse, and that would be the center of the circle. Okay. Now, if you have obtuse triangle, P is outside the triangle. Okay, but this is very important fact. Make sure you know this, okay? Because this is very useful information. In a lot of geometry problem, we use this knowledge to solve problems. So again, if you have a right triangle, then the midpoint is the center of the circumcenter. And also notice that from this point, from the P to here is your radius. From the P to this is also radius. But a lot of people kind of miss this, is that the P to the corner is also radius. See this over here? This is also radius. Okay? So remember that fact. Use that to solve the problem in the future. So again, the point P to here is a radius. To this vertex is also radius. Also from here to this right angle corner over here is also the radius. So this is the radius to all three sides, all three vertices.